let's do some guided practice with continuity. We're going to determine where the function is discontinuous, meaning where it's not continuous. And we're actually going to go one step further and talk about what type of discontinuity this is. It really just depends on what the graph looks like, right? So let's take a look. Right here we have rational expression, polynomial over polynomial, and one thing you want to note is that f of x equals, right, we always have to be careful whenever we're dividing by something, we have to make sure we're not dividing by 0. If we do this out, I think we're going to get x plus 4 times x minus 2 in the denominator. When we factor that, you'll see that that works. So we have potential issues, right? We have an issue with x equals negative 4, and we have an issue with x equals 2. So we will say f is discontinuous at x equals negative 4 and x equals 2. Now, one thing to note is that x equals negative 4 is an asymptote. It's a vertical asymptote. Is an asymptote. In fact, it's what's called a vertical asymptote. Right? That if you took the limit as x approached negative 4, you would have a non-existent limit, right? It would be infinite. However, I would say x equals 2, I guess I would say actually, I guess I'll say the graph y equals f of x has a hole at x equals 2. And what do I mean? Well, I mean that if you graph this, right, the graph is going to look something like this. Negative 4 is going to be all sorts of problematic, right? We're going to have this, whatever, then we might have this, and then at 2, we're going to have this. We're going to keep going, right? Because f is totally fine at every other point, aside from negative 4, of course, and 2, right? If we just cancel this out, we're totally fine, right? So we have what we call a hole, okay? Let's look at another example, right, number 2. Here, I think it's clear f is discontinuous at x equals 0, right? Because they were clearly dividing by 0, right? Clearly. And x equals 0 is, again, an asymptote, what we call a vertical asymptote. Okay? That's all there is to it. Again, if you were to graph this, it would be something along the lines of this, something like that. Okay. All right, you get that. All right, now what about f of x equals this piecewise function? Okay, well, we just take a look, right? The limit as x approaches infinity, x approaches 0 of 3x minus 7, let's say 0 from the left, right, is going to equal negative 7. Limit as x approaches 0 from the right of f of x is this guy. And oh my goodness, look, they equal the same thing. Now you might be tempted to say, oh look, f is continuous, right? Be a little careful with that. You're not wrong, but you haven't shown enough. This means the double-sided limit as x approaches 0 of f of x equals negative 7. This does not show f is continuous at 0. Pause the video and think about it for a minute. There's one thing we need to add. We need to add that this equals f of 0. This is the definition of continuity. Not just that the limit exists, but that it equals f of 0. Okay? So f is continuous really everywhere. Okay. Let's look at another example. Here we have another piecewise function, and we have that the limit as x approaches negative 1 from the left of 4x plus 5. Well, I think we can handle that. That's going to be 1, right? Negative 4 plus 5. We have the limit as x approaches negative 1. From the right of f of x is going to equal this guy. What is that? 1 plus 2 minus 6. And that's definitely not going to equal 1. That's going to equal negative 3. So the double-sided limit as x approaches negative 1 of f of x does not exist. So f is discontinuous at x equals negative 1. And in fact, we say f has a jump discontinuity at x equals 1. And what that means is that if we were to graph f of x, we're looking at negative 1. Actually, I shouldn't even do it. We don't have an asymptote or anything like that. But what we do have is we have, let's see, 4x plus 5. So it's a graph that looks something like this. This graph is at 1, right? So it's something like this. Let me make it a little steeper. Something like this. Okay. And then all of a sudden we have x squared minus 2x minus 6, right, which is going to be down here. Right, this is at negative 3. And it's going to look something like this. Right, so you see how we jumped down like that? It's not really an asymptote per se, but we just jumped down. That's a jump discontinuity. Okay. Now, in this case, this may not be obvious, but cube roots are totally fine. They have domain negative infinity to infinity. F is continuous everywhere. Right? It's totally fine. It's totally fine. Cube root is continuous. 5x minus 9 is continuous. Domain is legit. It's totally fine. And last but not least, let's take a look at this doubly piecewise function, right? We're interested in x equals 1. So first, let's see if the limit exists. The limit as x approaches 1 from the left of f of x is this guy. And it's going to equal negative 2. Limit as x approaches 1 from the right of f of x equals this guy, which equals negative 2. Okay. You might think, oh, f is continuous at x equals 1, right? Because the double-sided limit as x approaches 1 of f of x equals negative 2. However, actually, upon further review, f of 1 equals negative 3. So if you thought f of x, if you thought f was continuous at 1, you were mistaken. F is discontinuous, or you can also write not continuous at x equals 1. F has a, I'm just going to graph it for you, and you tell me what kind of discontinuity this is. Something like, well, let's see, 2x squared minus 4 before 1. So it's something like this. Oh, this is 1, right? So something like this, yep. And here's our negative 2. And then we have a little hole right there. And then we have negative 3 right here. And then we have negative 4x plus 2. So it's something like this. Let's graph y equals f of x. So what kind of a graph is that? That is called a hole. Right? A removable discontinuity at x equals 1. That's all I've got. Thanks.